We discussed another method of establishing a constant bias current in a transistor, that is source feedback biasing. We connect a current source to the source terminal of the MOS transistor. Okay. Now what we'll try to do is to realize a common source amplifier which incorporates this type of biasing. So our bias picture looks like this. The gate is biased at a constant voltage VG0 and a current source I0 is connected to the source and the drain is connected to VDD, because in the biasing picture the drain plays no role. The common source amplifier looks like this. The signal is applied between the gate and source, and the output is taken between the drain and source. This is the drain, this is the source, and this is the gate. Okay. And let me change the notation for the input. Let me call this Vi for the input signal. Okay. And the output appears between here, and this amplifier provides a gain of minus GM RL. Okay. From earlier experience, we know that we could have some extra components. It could be, for instance, from here to ground, and it could be from here to ground, or even elsewhere between the gate and drain for establishing bias. Okay, so those things may be there, that we will see. Now the question is, how do we bias the transistor like this and make it look like this for the signal picture? Okay, so that's what we have to do. So we'll take it step by step. Here we have used a voltage source here and a voltage source there. We don't want to do that. We want to use a single supply. Okay, so how do we do that? First part is very easy. To derive the gate voltage from this main supply voltage VDD, all I have to do is to use a resistive divider R1, R2, and this is a supply voltage VDD, and the gate voltage will be VDD times R2 by R1 plus R2, and we can set this to anything we want by suitably choosing the values of R1 and R2. Okay, then the signal source must be applied to the gate of the transistor. Okay, how do we do that? I won't spend much time on this. We have done this many times now. This part establishes the bias. To add the signal from this, what we have to do is Vi, Rs, and connect a coupling capacitor C1. Okay, now we have to be able to connect the load. Okay, and the drain cannot be connected to the supply voltage directly. If we do, okay, we know that we can connect the load to the drain by AC coupling, so that the DC value is blocked and only the signal appears here. But if this is connected directly to VDD, the drain is connected directly to VDD. VDD is nothing but ground in the incremental picture. Okay, so that means that this will be connected directly to ground. So if it is connected to ground, then the signal voltage swing here will be 0. Okay, so that cannot be permitted, obviously. Okay, we want some signal to come out of the amplifier. So the drain has to be connected to VDD through a bias resistor RD. Okay, it has to get connected somewhere, so that this I0 has some path to flow and it has to go to VDD, but it can't be connected directly to VDD, because in that case that is like shorting the output of the amplifier to ground. Basically, if we connect it directly to VDD, we will have a short circuit here, right, from the drain to ground. So then clearly the gain will be 0. It will be GM times the 0 resistance. Okay, so what we need to do is connect it through this resistance RD, and then if we do both of these, what happens is that we will have a resistance RD from drain to ground in the small signal incremental picture, and R1 parallel R2 from gate to ground in the small signal incremental picture. And this is the same as in a couple of cases we have seen earlier. The common source amplifier with constant voltage bias had exactly these things. Now you can see that one thing is still left out. Okay, there is one difference between this and that. The source of the MOS transistor must be connected to ground in the small signal picture. That's why it is a common source amplifier, so that the input is applied between gate and source, output is taken between drain and source. If you look at the source terminal of the MOS transistor in our actual circuit, it is certainly not connected to ground. If we draw the incremental picture from this picture on the left side, I0 will become an open circuit and the source is not connected anywhere. Okay, so if you do that, you can analyze it and see, and the gain will again be 0. So this has to get connected to ground for signals. And as usual, as always, we have made the assumption that signal frequencies has a certain minimum which is not 0. That's why we are able to couple the input through a capacitor, take the output through a capacitor, and so on. And we can use a similar idea to connect the source to ground for signals. Okay, when we say we have to connect the source to ground, essentially you can think of it as applying 0 signal. To the source of the transistor. Okay, so let's say I have a source that is 0 and the source of the MOS transistor has to get connected to this. Essentially it should get shorted to ground for signal frequencies. Okay, so that means that we have to couple it to the ground or the 0 voltage source through a capacitor. Okay, so that's what we will do. We will connect it to ground through a capacitor. Let me call it C3. Now as before, if the capacitor is sufficiently large, okay, what happens is that it will act like a short circuit and it's as though the source is connected to ground. Okay, we have to evaluate the criterion for C3 to behave like a short circuit. That we will do later. Okay, so what we did was the following. I went through this pretty quickly because by now you are familiar with the principles of AC coupling at the input and output. The only thing special here was with this biasing scheme, the source terminal of the MOS transistor is not connected to ground. In the drain feedback case, the way we started off, it was connected to ground, but here it is not. So we have to connect it to ground for signal frequencies through capacitor C3. Okay, so this circuit now is yet another topology of a common source amplifier. It uses source feedback biasing. Okay, I will redraw the circuit here. I have the signal source. It's AC coupled to the gate of the transistor and the gate is biased using a resistive divider which is powered from the supply voltage VDD, and the source is biased by connecting a current source to it. A path for the drain current is created to VDD through a resistor RD. Finally, we have to evaluate the drain source voltage of this transistor M1 and make sure that it is indeed in saturation region. And the load will be coupled through a second capacitor C2. And finally, the source of the transistor is shorted to ground using a capacitor C3. Okay. Now if I draw the small signal incremental picture of this, we will have the input source Vi, Rs, and it's connected through capacitor C1 to the gate of the MOS transistor. And from the gate of the MOS transistor we have these two resistors R1 and R2, and in the incremental picture this point here, the supply voltage is also ground because this supply voltage does not have any increments at all. Okay, so we will have R1 and R2 from this point to ground, in other words R1 parallel R2. Then we have our control source of the MOS transistor. This is VGS and that's GM VGS. This is the drain, this is the source terminal, and from the source terminal to ground we have the capacitor C3. Okay, this current source is an open circuit because it's a fixed current source, and from the drain to ground we have RD and the capacitor C2 and the load resistor RL. Okay, so this is the small signal incremental picture, and we have to make sure that C1, C2 and C3 are shorts at the signal frequencies. Okay,